Welcome, everybody. Today, Sangman Lee from CU Boulder is going to talk about subpower intersection problem for finite semi. Please, Sangman.
Hi, thank you for the invitation and thank you for organizing PALS talk. Let's begin with the motivational problem, the subpower membership problem. So in 2007, in connection with the universal algebraic approach to CSPs, Iziak and his colleagues introduced the subpower membership problem. So the subpower membership problem is the following problem. So SMP, let S be any fixed finite algebra, and SMP has input, which is the set A of n tuples over S, and the target element B of n tuple, target element B, which is an n tuple in the same set S to the n. And the problem is the target element B in the subalgebra generated by A. And this has been studied thoroughly, and there are a few results on SMP. And for vector spaces and groups, SMP is in P, as proven by Willard. And for Mall subalgebras, it's in MP, proved by Peter. And for semigroups, it's in P space. It's also proven by Bolotur, Kozik, Peter, and Stendel. And for general algebras, it's in exponential time. And Kozik actually constructed the exponential time example, exponential time complete example. Let me actually move this thing. Sorry. Let me actually try to move this. Oops. Yeah, this bar is a little bit bothering. Okay, let me put it here. Okay. All right, so the subpower intersection problem, it's a related problem to subpower membership problem. It has inputs, set A and set B of n tuples over S. And the problem is the subalgebras generated by A and B have any common element. And you might notice already for algebras with null operations, SIP is trivial because it always have a constant element. So we're interested in subpower intersection problem for the algebras without null operations. And in this talk, we'll talk about SIP for finite semigroups. There's another related problem. It's the idempotent target subpower membership problem. Because I don't know how to remove this thing. Yeah, it's always annoying. Hide meeting, maybe?
No.
Oh, okay.
Saying that it does not show up.
Oh, it doesn't show up.
So it's
The projections,
Yeah.
it's just blurring.
Bottom, yeah. Yeah, maybe
Put
that's
it in.
Yeah. Okay, then I don't have to worry about it. So the idempotent target SMP is the problem, the following problem. So again, you let S be a finite semigroup, and input you have a set contained in a set of n tuples over S, and you also have a target element E, which is an n tuple restricted to idempotents. And the problem is E contained in the set, the algebra generated by A, in this case, sub-semigroup generated by A. And you can see that this is immediately polynomial time reduces to subpower membership problem, but also this also the idempotent subpower membership problem reduces to the SIP. So this is a quick picture how the problems are related. So you can see that IDSMP reduces to SIP and also reduces to SMP. And there is a little connection, some connections between SMP and SIP. And if SMP is an MP, then SIP is also in MP. But there is no general polynomial time reductions from SMP to SIP or vice versa. So here's a general complexity result for SIP. So here's the theorem. SIP for any finite semigroup is in P space. To prove this theorem, we use the same argument as in the proof of SMP for any finite semigroup by Bolter and his colleagues. Essentially, we show that this SIP is in non-deterministic linear space, and by Savic's theorem, it's contained P space. And for also another general complexity result is that SIP for transformations semigroup with more than 3 elements, over more than 3 elements, is P space complete. And this one was actually free from Bulatov and his colleagues, because they showed that the idempotence of power membership problem of T3 is P space complete. So since IDSMP reduces to SIP, SIP is also P space complete. Okay, so before the main result, we'll go over some definitions. So here's some semigroup definitions. So let S be a semigroup, and E of S means the set of all idempotents in S. And a band is a semigroup consisting entirely of idempotents. So everything is idempotents, then we call that semigroup a band. And a semilattice is a commutative band. And finally, a normal band is a band where the middle terms commute. So you can see ZXYZ equals ZYXZ. So you have a middle term commutativity. So that's the normal band. So the main result for one of the main results for this talk is the dichotomy for bands. And let S be a finite band, then the SIP is in P if S is normal and MP complete otherwise. So I'm gonna quickly do proof sketch for both cases. But first we're gonna talk about why SIPS is in P if S is normal. So SIP for any finite normal band is in P, but the idea is this problem, SIP for finite normal band, reduces to cases where the input sets generate semilattices, and given AB in any normal band, any subset in any normal band, any generating set in normal band, if they have common element in their generating sets, if we fix the first element and last element, they become a semilattices. So using this fact, we're able to reduce the subpower intersection problem for normal bands to polynomial many instances of the restricted problem where the input set generates semilattices. And so all we had to come up with is the algorithm that solved this restricted version of individual small problem instances. And I don't want to go through all this algorithm, but this is the algorithm we discovered. And for non-normal band case, that's actually where I think it's more interesting. So to show that SIP of S is MP complete, we had to show for non-normal band, we had to show that SIP for the E of T2 is MP hard. So E of T2 is idempotence in the transformation semigroup over 2 elements, and it's just 0, 1, and identity, and 0, 1s are right 0 elements. And the key lemma that we proved is that SIP of E of T2 is MP hard. And with this fact, we also show that every non-normal band contains either E of T2 or opposite semigroup of E of T2. So that shows that SIP for any non-normal band is NP hard. And we use the Stendel's fact that SIP for any finite band is SMP for any finite band is in MP. So SIP is also in MP. So combining all this fact, we proved that SIP of any non-normal band is NP complete. Okay, so I want to talk about the key lemma. Of course, I don't have enough time to prove all this key lemma in detail, but I want to show some example. Why does this reduction works? Why is it NP hard? And but one thing it's interesting is that for the set containing 0, the right 0, and ID, and the right 0 element 0 and 1, the subpower intersection problem is in P. It's really relatively easy to show it's in P, but as soon as you add one more element, either constant or the identity, the problem becomes NP hard. And we show this fact by reducing 3 set to SIP. So here's the 3 set given clauses with the 3 terms, C1 through Cn, is the formula satisfiable. That's the 3 set. So here's the sort of the pre-proof sketch for the key lemma. So given 3 set instances, phi with n clauses and k variables, we construct an instance of SIP E of T2, so only using 0, 1, and ID, with the sets A and B in E of T2 to the 4 to the n. So it's a polynomial time reduction. And then we show that essentially we show that phi is satisfiable if and only if the intersection is non-empty. So really the big question here is that, so how do we encode this formula phi into A and B? And this is the, not a proof, but it's an encoding example for the key lemma. And this is essentially the idea why the proof works. And so for example, given 3 set formula, so x1, x2, negation of x3, so on and so. And you have 2 clauses and 3 variables here. So we work in E of T2 to the 4 times E of T2 to the 8. That's the place we're going to construct the encoding of this formula. And one satisfying example in this formula is so you now write down the normal form for this formula, so which is x1 comma x2 and negation of x3, and negation of x1, negation of x2, x3, and which is just writing down the exactly how the terms, the variables are in the clauses. We just write that down, and we encode this 3 set instance to the in AB, and you can see. So the idea is that on A you generate all the encoding of formula that makes the formula satisfied. So there are 7 ways that a formula can be satisfied, and the examples are 0, 0, 1, and 0, 1, 0. Oh yeah, so yeah, it's so good. 0, 0, 1, 0, and 1, 1, 1, and so that's our sort of the goal, so that our formula will be satisfied. You can see that here. And so we on the left side we have A11, and on the right side we have A21, and the A1I encodes all the ways that the first clause can be satisfied, and the A2I encodes all the ways the second clause can be satisfied. On B, we evaluate it's an evaluation of the term. So what B encodes is that all possible evaluations. So B10 means that you're evaluating the first term with 0. And the B20 means that you're evaluating the second term with 0, and so on. And B11, same idea. You evaluate the first term with 1, and then you evaluate the second term with 1, and so on. And you can see that you can see when you have the correct element, so if you have an intersection, so in particular here, you have an intersection B10, B20, B30, and then A11, A21, then phi is satisfiable. So that's the idea for the NP completeness. And using this thing, we can now prove that SIPT2 is NP complete. So NP hard comes from the fact that E of T2 is NP complete. And then in NPness, we show that SIPT2 is an NP using the fact that SMP T2 is in P, which means it's an NP. And this fact was shown by Bolter and his colleagues. Okay, so for the next result, we need a few tools beforehand. And the first tool we need is the idempotent separating congruences. So let tilde be a relational semigroup. And we say that tilde is idempotent separating if no two distinct idempotents are related. So if tilde is an idempotent separating congruence, then we can have SMP of SIP of S reduces to SIP of the S quotient tilde. And a proof of this is not really too difficult. You use the fact that if there is intersection in the quotient, then you take the idempotent power of each element. But since idempotents, this relation is idempotent separating, they must be actually equal in the original semigroup. And there's another notion that we need to take from the Rees. So this is a Rees matrix semigroup. And by Rees theorem, he showed that every finite simple semigroup has the form that S can be written as triple of some indices and group element. So he uses this notation, MG G as a group, and the I and lambdas are the indices, and P is the matrix that encodes the group elements. We call this sandwich matrix. And the Rees matrix semigroups are defined as these triples, and the multiplication is essentially you have two elements, the I, G lambda and J, H mu, that we just take the first indices and the last indices from the second element. And for the group element, we multiply G and H, but with the sandwich matrix in between. So elements from the sandwich matrix in between. And then the elements, you take it from lambda row and then J column. So what's interesting about this is that the H classes are this set of the elements with the indices, I and lambda. And the quotient of this H mode H quotient H is rectangular band because we don't care about if you quotient it, then the group elements coalesces. So it's a rectangular band, and that means it's a normal band. And another fact about this is that if S is group, if lambda and I, the size is 1, then obviously you only have the group multiplications, so it's a group. Okay, so here is the another result that we proved for finite simple semigroups. So if S is a finite simple semigroup, then subpower intersection problem S is in P. And this is just directly from the idempotent separating congruence. So we take the quotient, and since the quotient is a normal band, so SIP of S is in P. And there's now interesting theorem here. So let S be a finite simple semigroup, then SIP of S to the 1 is in P if S is a group, and otherwise SIP of S to the 1 is NP complete. And this S to the 1 means that adjoining identity if necessary. So for example, if S is a group, then if there is already an identity, so S to the 1 is S. So since we proved that in the previous case, so if S is a group, then SIP of S to the 1 is in P. Now, if S is not a group, then we prove that SIP of S to the 1 is in NP by extending the Green's H relation to S to the 1. And then we prove the hardness by showing that this S to the 1 actually has a copy of either e to the ST2 or e to the T2, the opposite semigroup of e to the T2, but both would give NP hardness. So in NP, am I doing well on the time? I think so. So in NP, we extend the H relation to S to the 1 on S to the 1 by this relation. So if they're both 1, then they're related, or if they're H related, then we say that it's related. And since H was already a congruence on S, so the relation S is also a congruence on S to the 1. And each H class in S contains a unique idempotent. It's an adjoined identity alone because it's its own separate tilde class. So it's congruence as well, and it's idempotent separating. So so that means we can use the previous lemma about that, the fact that SIP S to the 1 reduces to SIP S to the 1 quotient by the tilde. And the quotient S to the 1, the quotient is the H quotient with the identity adjoint, so it's a finite band. Therefore, it has an identity, and it's a finite band. And then Stendhal actually showed that for any finite band, SMP is an NP, so SIP is also in NP. For NP hardness, we dig down and we actually find the elements that are isomorphic to E of T2 or E of T2, the opposite group of E of T2. But yeah, it's essentially the same idea, but it just we just find the correct elements. I think for the time being, I think I'm gonna skip, but yeah, it's same idea for E of T2 and E of T2 or P. Okay, so for the next, another main result, I want to talk about combinatorial Rees zero matrix semigroups. So it's the same Rees matrix Rees matrix semigroups, but now you can only take group to be the identity group, a trivial group, and then your matrix P to consist only zero or the identity in the group. So if you take this, then you can actually simply write down this as the pair of the indices, I and lambda, and multiplication is defined as taking, if multiply two non-zero element here, then you just take the first indices and the last indices from the second element. And if the lambda j is in the sandwich matrix is 0 on the lambda row and then j column, then we define that to be 0. And if it is 1, then we just multiply normally. So one I think familiar example would be Brand semigroup. So Brand semigroup, we have a sandwich matrix 1, 0, 0, 1, and it has exactly same structure as a Brand semigroup. Okay, another condition here we need to talk about is the one block condition. So, so for the sandwich matrix, the grid of 0 and 1s has one block if there are subsets delta in lambda and j in I, such that everything in that subset is 1, and everything else is 0. So equivalently, it's just the the one entries in the sandwich matrix form a single rectangle in the sandwich matrix, and there is everything else is 0. And now we have another result. So now let's say let S sub p to be a finite combinatorial Rees zero matrix semigroup. Then we have trichotomy for SIP of S sub p to the 1. If the sandwich matrix P has one block and has at most one entry, and one block, then in that case, we know that the SIP of S sub p to the 1 is in P. And if P has one block and at least two one entries are there, then we know that SIP of S to the 1, S sub p to the 1 is NP complete. And if P doesn't have one block, then SIP is P space complete. So here is an example of S sub p to the 1. So the Rees combinatorial Rees zero matrix semigroup adjoined an identity, which is the Brand monoid. And the Brand monoid has, it doesn't have one block, because you can see that the sandwich matrix of Brand monoid has two blocks. There's one here and then another one there. This is doesn't form a rectangle. It's not one block. Okay, so for the proof, we basically prove individual cases. So one block and at most one entry. We use a Rees factor semigroup. So for an ideal, given an ideal of the combinatorial Rees matrix semigroup with 1, the Rees congruence is essentially identifying all the ideal elements into sort of 0 element. So the quotient with this relation, and usually written as quotient by I, the ideal is a Rees factor semigroup. And if P has a unique one entry, we write it as P of lambda I equals 1. So then I lambda is the corresponding idempotent in the combinatorial Rees matrix semigroup. So there are actually two cases because you could have 0 one entry and 1 one entry. So if you don't have any one entries, then the Rees congruence gives this. So the ideal is the wait a second. Oh yeah, ideal is SP. Sorry, yeah, SP. And then the quotient is the ideal itself and the identity one. So you can see that this one SAP of I and 1 is in P. And similarly, you take ideal when you have one entry, you take the ideal, the Rees matrix semigroup without one, and minus this the unique idempotent, which is the I lambda. And then we have, when you multiply by that, we have I and I lambda and 1, and that is also in P. So because this Rees congruence is idempotent separating, the Rees factor we can now say that the SAP S sub P to the 1 reduces to SAP S P to the 1 quotient I, and they both are in P. Okay, so now the second case is when you have a one block and at least two one entries. In this case, if you have one block and at least two entries, then also kind of same idea. You construct, you dig down the matrix and then you construct, you find a copy of E of T2 or a copy of the opposite semigroup E of T2 inside S P to the 1. And hence, SIP in this case is NP hard. And for containment NP, again, we use the standard result that SMP of S to the 1 is an NP whenever P has one block. Okay, when you don't have not one block, then in this case, we reduce the cosine composition function composition problem, which is a P-space complete problem. But standards show that this cosine composition problem reduces to SMP over this combinatorial Rees matrix semigroup, with 1. And we take he showed this using his own instance, SMP instance. And what we did is we showed that this Stendel's instance can be also encoded as an instance of the idempotent target subpower members problem. And with this encoding, we were able to show that the cosine composition problem reduces to SMP and SMP reduces to idempotent target SMP. And now we know that idempotent target reduces to SIP. We have shown that SIP of combinatorial Rees matrix semigroup with 1 is in P-space hard, and general it's in P-space, so it's P-space complete. Okay, so before ending the talk, I would like to compare the subpower members problem and subpower intersection problem, because I thought I felt in the beginning I felt they are very similar, but actually it turns out they're actually sometimes SMP is easier and sometimes SIP is easier. So for bands, standards show that SMP for bands is in P if and only if his quasi identities hold, and otherwise NP complete. But in SIP case, bands is in P if S is normal, and otherwise it's NP complete. And for commutative semigroup, in this case, SIP is easier problem because SIP of commutative semigroup is in P, but SMP, it could be NP complete depending on the semigroup structure. And for some well-known semigroups like Clifford semigroups, nilpotent semigroups, and simple semigroups, they are both in P. But for simple semigroup with a joint identity, SMP is actually open, but for SIP, it's in P if S is a group, and otherwise NP complete. And another, so the completely regular semigroup, both SMP and SIP are open, but for the transformation T2, in this case, SMP is actually easier. In this case, SMP is in P, but SIP is NP complete. Okay, so and then there's a also I thought this was pretty interesting comparison. So for combinatorial with zero matrix without one, so SP, it's in P if and only if P has only one block, and it's then to show that it's SMP is in P if and only if P has only one block, and otherwise NP complete. But SIP we weren't able to show. But for the Rees matrix semigroup, a combinatorial Rees matrix semigroup with one, it's in P. Stand to show that it's in P for all one matrices, and NP complete for one block matrix with 0, and then P space complete when you have more than one block. And we have a similar classification, but somewhat different. So it's in P for one block matrices with at most one entry, and NP complete if you have more than one entry, more than one entries, and P space complete when you have more than one block. So here is a quick picture. How does Stendhal's trichotomy for SMP of the combinatorial Rees matrix semigroup with one? So if you have if you don't have one block, so if you have more than two blocks, it's P space complete, shown as red color. And if you have a one block, but if you have at least 0 entries, then it's NP complete. But if you don't have 0 entries at all, then it's in P. But in SIP case, so trichotomy for SIP, so in this case, P space complete case is same, but for when you have a one block, but if you have more than one entries, then it's NP complete. But if you don't have, if you have less than or equal to 1 entries, then it's in P. So I thought it was a pretty interesting picture. And I have a few open questions about this project. So the first question is SIP for finite completely regular semigroup is an NP? I'm asking this, we're out of time, I guess. Yeah, I was wondering about this because Stendhal also couldn't show that he was actually had an open question about this as well. So both SMP and SIP for finitely completely regular semigroup is open. And the next question is SIP for combinatorial Rees matrix semigroup is in P or NP complete? And then finally, does the idempotent target subpower members problem have a trichotomy, just like the SMP and SIP for SP to D1, but maybe it could have P space dichotomy. But we know that it's at least there are some instances where it's a P space hard, but we are not sure that if it has like a nice trichotomy or dichotomy. And that's the end of talk. Thank you very much for giving me the opportunity to talk.
Thank you. Thank you.